Thank you very much, Aldo. Okay, thank you everybody for coming. First of all, is there any announcement? Anything? No? Okay, so, well, it's my pleasure to welcome here today to the Institute to Professor Nina Hatch. Nina did her PhD in the University of Cambridge and finished in 2007, and then moved on to do a postdoc in Leiden. Then she went back to the UK and to Nottingham, where she's a professor at the University of Nottingham. Her interests are basically, galaxy clusters, as what she's going to tell us today. But from protoclusters to the cooling flows in galaxy clusters. She is very involved in the Euclid collaboration, in the Euclid mission, and specifically, she leads a working package on intracluster light, and that is what she's going to tell us today. So thank you very much, Nina, for coming here, and the floor is yours.
Thank you. Are you going to give me a wave when I'm running over? No. Okay,
yes. You're free to go.
I'll keep it within time. Okay, thank you for coming to see me today. So the advertised talk title, I think, was Euclid's view of intracluster light. I'm still going to be giving you Euclid's view on intracluster light, but as I was writing this talk, I think Euclid has a very broad view of intracluster light. So I've just narrowed it down to this idea of, can intracluster light tell us anything about the nature of dark matter? This is work I've done with my group. So I've got two students, Joe Butler and Adela Begnas, and then a series of postdocs, and I'll be highlighting their work as I go through it.
Maybe rest.
There we go. Okay, so why this question of figuring out what dark matter is? So it's the dark matter is the dominant component of matter in our universe, and yet we know virtually nothing about it. And this is the big problem. We know it's non-baryonic, but actually, does it interact with itself? Does it interact with matter at all? We just don't know. And so this is the major question that I'm going to be trying to answer today. The one thing that we do know is that the dark matter particles, whatever they may be, assemble hierarchically. They form into these halos, and then these halos merge, and they build up structures. So they start from tiny dwarf galaxy halos up until the big cluster halos that we see situated with the cluster galaxies. Now, I'm going to argue that the structure of these halos are really informative about what the dark matter particle actually is, or the properties of the dark matter particle. So I'm going to be concentrating on just self-interacting dark matter as a type of dark matter particle. And these are two simulations of the same cluster-sized halo, so really massive. I mean, you're just looking at the dark matter. But in this simulation, you've just got your concordance cosmology, cold dark matter. And in that simulation, it's SIDM, stands for self-interacting dark matter. It essentially means that dark matter particles have some cross-section, so it's a non-negligible chance of interacting with other dark matter particles, but it doesn't interact with any baryonic particles. Now, we know that dark matter can't be, highly interacting, but within our observations, it's perfectly reasonable that dark matter will interact with itself or with dark energy, or even with baryons to a small set fraction. In fact, every direct dark matter detection experiment actually assumes that dark matter does interact with normal baryons, right? Because it hits the nucleus of a normal atom and we see that recoil. So, or we do assume that dark matter can interact with other matter at some level. So, but a cold dark matter, this model says it doesn't interact at all, and that one, it does interact a little bit. And hopefully you can just see by eye that there are differences in the shape of these halos, right? So in your cold dark matter, the main differences are in the core of the halo, you've got a highly peaked region. This is what we call cuspy cores, NFW profiles, which is the profile of this region. They sort of end up with a very high peak. Self-interacting dark matter, instead, you see at the center, it's actually quite fuzzy, and that means that the core is quite flat. You've just got, and it's just because the particles are interacting in that region. The other thing that you may notice, I think what's quite clear, is that there's less substructure, so there's less of these small halos. But another thing is that this pink region, you can hopefully see, is actually more round than this region, right? And so that's another impact of the self-interacting nature of dark matter. And so you can see that if dark matter interacted with itself, if you can measure its cross-section of interaction, we would see different halo properties. So here is, I mean, there are many, many papers on this. So here are some plots showing just the level of that difference. So this is an early work in which it showed you the profile, so the density of the dark matter against the radius, and the black line is whole dark matter, and then you've got different versions of the self-interacting dark matter. You can see over here the profile is identical, but over here you can see there's a difference in the profile. Here's that chord profile, the sort of flat. And you also have a very recent paper which discussed the axis ratio. So if I just go back, your axis ratio is the, say this is the major axis, so it's the ratio of this axis length over this axis length. And you can see for an interacting particle, the halos tend to be rounder, so an axis ratio closer to 1 compared to cold dark matter. I've only been talking about self-interacting dark matter, but there are a wide variety of dark matter models. You can have fuzzy dark matter or axions or all of these different models of dark matter. Because we've got so few constraints on it, theorists can come up with almost anything to satisfy it. And they all have a whole swathe of papers telling you how the halo should look. I'm not going to show you all of that. I'm just going to sort of say that the halo properties differ from cold dark matter. Another thing, so measuring the shape and the profile of the dark matter tells you about it, but so does something called BCG wobble. So BCG stands for brightest cluster galaxy, and it's that galaxy at the center of a cluster. Now, David Harvey's been working on this and basically says that if you have, let's put this down and have a little experiment here. You've got a massive cluster and your BCGs at the center of your cluster, and then there's a major merger with, say, a galaxy group. That's going to kick your brightest cluster galaxy off its equilibrium in the center of this halo, and it's going to basically oscillate around the core. Now, if cold dark matter is, if matter is cold and dark, then it will be very highly peaked. And so the brightest cluster galaxy will wobble very quickly, but very quickly settle into the equilibrium. So after a merger, you wouldn't see it very far from the center of the cluster. If the profile is cored, once you kick that galaxy from its equilibrium position, it will just oscillate for a very long time and with a large amplitude. Now, how cored your profile is, if it's with some very high self-interacting strength, then you're going to have this red curve. And so you're going to get quite large dark matter offsets. So you're going out to about 20 kiloparsecs even, you can measure. Cold dark matter, we would only measure about 4 kiloparsecs difference. So let's just emphasize that my goal is really to just measure the shape of these dark matter halos, the profile, the shape, and see if there's any offset. and then compare them to our expectations of cold dark matter. And by that, doing that, see if I can determine anything about the nature of the dark matter particle. Now, most people, I'm going to set this video running. Yeah. So most people have started looking at this using lensing. Lensing is a very powerful tool for mapping the matter, but I'm going to argue that actually intracrustal light is possibly an even better tool. And if it's not even better, it's at least a tool that has different systematics. And so if we are able to measure the shape and the profile of the halo with lensing, we should get the same result with intracrustal light. So what this movie showed you, it was from the hydrangea hydrodynamical simulations from Yannick Bahe. We've gone past redshift 3, but it started off showing you redshift 3. Above, it was gas particles. And then once it got lower than redshift 3, you started seeing stars. And what you're seeing is the assembly of a fairly massive cluster going on. And I want you to notice these big things, sorry, I'll get out of the way, as they come in and how stars are being stripped of them as they fall in. So you see it fall in and all of these stars get ripped off. There's more stars being ripped off there. Now, those stars that get ripped off the galaxies, they are no longer bound to those galaxies, but are instead bound to that large intracluster halo, the dark matter halo. And so basically they are bound to the halo, and so they should trace the dark matter halo. Now, how ICL forms, I'm not going to talk too much about this, but I just want to emphasize that there's quite a lot. So this has come from Maria's sort of review, which was in Nature Astronomy, that actually there's lots of different types of ways in that intracrustal light can be produced. This one, in situ star formation, is quite controversial because half the simulations, I think it's the one using SPH, they find in situ star formation. People using grid-based codes do not find any in situ star formation. So it depends which type of, or it might be the other way around. It depends which type of simulation you use. But I just want to emphasize that the dominant way intracrustal light forms is basically these things: major mergers and stripping of very massive satellites. And it's just because that's where most of the stars are in the universe. They sit within these massive galaxies and they combine to form the intracrustal light. So why should this intracrustal light trace dark matter? Well, let's think about the halo. At the center, you've got your galaxy. Now, the stars that make up your galaxy actually cooled and condensed out of gas. As that gas cooled and condensed, it shared angular momentum and energy. And so basically, it doesn't have any idea of what the large-scale halo, the angular momentum or energy of the large-scale halo. However, the stars that sit out here, they were formed through those accretions, through those massive galaxies coming in, being stripped of their stars and forming this large halo. Now, that's exactly the same mechanism in which the dark matter halo is formed. And so therefore, we would expect both the intracrustal light and the dark matter, since they've assembled through the same process, they should have the same energies and distributions. Finally, why do I think that intracrustal light is a good tracer of halos? It's because Maria told us it was and showed us it was with observations. So we have empirical evidence that it does. So this is her work on the Hubble Frontiers fields. Really embarrassing presenting this when she's right there. What she did is that she mapped out contours of the intracrustal light in green. The mass comes from the lensing, so she's got contours tracing the mass, and then the X-rays, she's got contours from in the red. And she showed that in all of the Hubble frontier fields, the mass contours and the ICL contours were very well matched. It was absolutely excellent. And so this was sort of the first real empirical evidence that intracrustal light does trace mass. So it does look like we can do it. So what did I then do? So this paper, before I saw this paper, I was working on protoclusters, really high redshift clusters. I was trying to understand how clusters formed. And then I saw this and I thought, this is actually really exciting. So I changed a lot of my field of research and started doing intracrustal light. Yes, you are to blame.
Sorry.
Yeah. It's a lot harder than I thought it was. But anyway, so what did we do there? Okay. This is work that was published earlier this year by my student, Joseph Butler. So the first thing we did is we're waiting for Euclid to actually start taking data at this point. And we said, right, let's go to the simulations. We think that the intracrustal light should match the dark matter. Let's prove this with the simulations. And that was Joseph's task. And Joseph came to me very upset to say it really doesn't work. And let me talk you through why. So we took the Horizon AGN simulations. These are, there's only 12 clusters, fairly small hydrogen dynamical simulation. The reason why we started with this is that you actually need a very good dark matter resolution to simulate intracrustal light. If your dark matter particles are too large, when the mergers happen, the dark matter halo instantly evaporates, and then the galaxy instantly evaporates because there's nothing holding it together. So if you want to simulate intracrustal light, you need high resolution, which is why we're kind of limited at this moment. So here we have the intracrustal light and, well, all the stars, the stellar particles, and here's all the dark matter particles for a single one of those clusters. He then separated out the stars with their subhalos from what is the intracrustal light, the BCG, and the main halo here. And so we threw out these things, and we're just exploring what's the relationship between the stars and the dark matter in this main halo. And here he's plotted the energy ratio. Ignore this axis for now, just concentrate on this bit. And what I mean by energy ratio, it's the ratio of, in pink, we have the energy ratio of galaxies compared to the dark matter. And in green, we have the energy ratio of the intracrustal light compared to dark matter particles. So if we just start with the galaxies, it seems that the galaxies, if you look at their orbits, they have the same energy as dark matter. They're about 1. Now, what this actually says is, because I don't really believe the central region, I've cut out the central 100 kiloparsecs. And then I look at this dot. And then if I cut out 200 kiloparsecs, I can look at this dot. And 300 kiloparsecs, so just looking at this region all the way at there. So it doesn't matter if I cut out the central region, my galaxies match the energetics of the dark matter. This is great. We've been using the Viral theorem to measure cluster masses for ages, so thank goodness that works. This was really surprising. So what this is saying is that if we actually just took all of the light in the BCG plus the ICL, so brightest cluster galaxy plus intracrustal light, then the energy in the orbits of those stellar particles is only about 55% that of the dark matter. But of course, in the center, you've got your brightest cluster galaxy, and that comes from gas that's cooled and condensed. So we went further out. 100 kiloparsecs, you should have almost no brightest cluster galaxy, and still we have a lower energy. At 300 kiloparsecs, there's no chance any of that is called stars. It must all be stars that are stripped. And yet, the conclusion of this, and it took us ages to get it out, is that intracrustal light does have lower energy than the dark matter particles. So although they trace the same matter potential, they're on lower energy orbits. We'll come to why in a minute. The other thing that he measured is the anisotropy. So anisotropy is a measure of, for an orbit, the particle going in an orbit, what is its transverse velocity relative to the cluster to its radial velocity. So basically, if you have a high value of your anisotropy, then your orbits are more radial, you have low angular momentum. If you're down here with 0, then your orbits are more circular. And so your dark matter is in purple, and you can see as you go further out, your orbits become more radial. That's well known. The galaxies seem to trace the same kind of orbits as the dark matter, but the intracluster light have lower angular momentum and are on more radial orbits. So I spent the first part trying to tell you that intracluster light does trace dark matter, and now it seems I have to tell you the truth that it isn't a direct tracer. So if they have different orbital energies, what this means is that they're going to have different profiles. So this is the profile of dark matter, and then this is the profile of the intracluster light. And you can see that it is actually offset. And this is seen in the observation. So this is well known in the observation before we made this measurement. This is the cluster observed with JWST, and then here are the intracluster light measurements, this profile. The blue dots are the globular clusters profile, so they match very well. And then from the lensing, you've got this mass profile. You can see the difference in these profiles. So there is quite a clear difference. If only we could understand why the energies differ, then actually we could just use this known relation. So if we took this line divided by this line, we actually have a straight line. We have a power law, and all of the clusters seem to have the same. So it does look like that there is a well-known relationship between this and this profile, but we need to understand why. So I've showed you things about the profile. What about the shape of the halo? So this is my other student, Adela Ferdinand. She's been working with the hydrangea simulations and Horizon AGN. She's been measuring the shape of the dark matter and intracluster light. She fits ellipses basically by calculating the moment of inertia in a radial, in an annulus, and that allows her to get the best fit ellipse. And there's two things she found. First of all, your position angle, so the angle of the major axes between the dark matter and the ICL is very well matched. So this is the difference in those position angles. And if I just show you the 50% line, so almost, well, about half of the clusters that she measured, their angles matched to within 4 degrees, which is really nothing, all the way out. And then 75% of the clusters agree to within 10 degrees. And in the inner region, they agree extremely well. The other thing she did was compare the axis ratio. So it's the B axis, so minor axes over major axes. And you can see here that for the intracluster light, we have a slightly more elliptical shape than we do for the dark matter at all scales. So this comes in from what I was telling you before. The orbits are on more radial orbits for the intracluster light, and that means they end up being slightly more elliptical in structure. But although they're slightly more elliptical, they are very close in shape. It's really only a tiny difference. And this is why when we go to the observations and compare the contours, they do seem to match, because we're smoothing over such a small difference. Right. I wanted to just say, so I'm about to move on to the Euclid observations, but I just want to emphasize that what I've showed is that intracluster light isn't a direct tracer of the dark matter. I have to understand why it's not. And this is currently work in progress, so I'm not going to talk too much about it. But in order to try and figure out why they differ, we've got away from the cosmological simulations and started doing just idealized simulations. So here we have a brightest cluster galaxy in the green, surrounded by a dark matter halo in the purple, and we're throwing in a satellite, a very major merger satellite galaxy. And then we can see as it comes in, the dark matter gets stripped first, and then the stars get stripped. And we can see down at the bottom here, this is the energy ratio of just the stripped material of the star's dark matter. And you can see it slowly decreases from 1. This is because dynamical friction. And then here it suddenly goes. So when it starts doing this cycling in, there seems to be a major transfer of energy from the stellar particles to the dark matter particles. This is a work in progress. We don't quite understand why, but I'd be really interested to hear about people who've done similar situations on mergers, because this must have been done before, we think, and we'd really like to understand why this transfer occurred. Okay, on to the observation. So most of the time I am an observer. And one of the reasons I decided to get into the intracluster light was because I knew Euclid was going up. And although its main mission is cosmology, doing so through weak lensing and redshift space distortions, it's actually a really good intracluster light detector. And that's because it's above the atmosphere, and so you really can constrain your background there. I'm going to be talking to you today about what's known as the Quick 1 release. So this was released March, really recently. Yeah,
The public, yeah.
Thank you. I really should have known that. So it was released very recently. It's only 63 square degrees. So actually all of Euclid should do this region and a little bit of this region. But today all we have is that yellow blob, this yellow blob, and that yellow blob. And in those blobs, actually no cluster catalogue was available. So in fact, we had to leave out the northern ecliptic pole region and just concentrate on the other 2 regions where we do have cluster catalogues from DES, so that's an optical cluster catalogue, and eROSITA, which is an X-ray cluster catalogue. And so you can see the clusters I'm going to show you today, they go from redshift about 0.1 all the way up to about redshift 0.7. I've drawn this in terms of radius. It's R200 rather than its mass, but basically things between here are very sort of between 1 and 3 times 10 to the 14 solar masses, and then you've got a handful of things that go all the way up to 10 to the 15 solar masses. So we're mostly at the level of low mass clusters, the bigger groups. And we have about 150 to 200 clusters. We've had to throw out about 50 of them because they were too near bright stars. So this is what a cluster looks like as seen by Euclid, fully processed. This is what the data looks like if you just take it out of the archive today. So there's lots of steps that we've gone into actually fully processing the data for low surface brightness. And I won't bore you with the details because I want to get more into the science. But essentially for cosmology, we want to subtract all the backgrounds. And that means over subtracting any diffuse light like we see here. There's a very good reason for that, is because this is what the data looks like if you don't subtract that background. You end up with large blobs and features everywhere. And it's easier to just do a local background subtraction to get rid of these features. However, if we want to keep the intracluster light, we've had to do modeling of this large scale persistence and then subtract that off. The other thing we've had to do is all the detectors have a different bias level, even after the bias correction. And so we have to do some detector discontinuity correction. So this is what it would look like if you didn't do that large scale background, small scale background subtraction. but this is how we corrected for it. So now we can see the intracluster light around that region. And so that's our final product. We actually, it's too much to process the whole of the Euclid data. So we're just processing cluster by cluster as we see them. So it's a slightly different processing that's available for the large field. Okay, so then how do we measure the intracluster light? We identify our brightest cluster galaxy, and then we mask in pink all of the surrounding high surface brightness light. But you can see there are still some features that remain. And that's why we use this tool, AutoProf by Connor Stone, to measure elliptical isotopes around this intracluster light. And that's because it's a very clever tool that allows us to ignore these regions where there is sort of leftover light over here. It doesn't count it, it just measures, it does some sigma clipping to measure just the average flux in the annulus. We're able to measure the position angle and the ellipticity. So the ellipticity is 1 minus the axis ratio, out to about where the signal to noise is about 10. After that, it just fixes the value to the last value, and so that's why these are constant, but we can still measure a flux in this annulus. So about there, the position angle and the ellipticity are fixed, and then beyond there, we're just taking the same thing. So we can measure an ellipticity, so we can measure the shape out to this point. So this is our first result from that. We can measure the shape in all the bands, all the filters in Euclid. And this is the mean shape of those 150 clusters that we were able to get out. So I'll just, I think, just look at the red dots here. So this is the H band. What we can see is that the ellipticity, so it's 1 minus the axis ratio. So down here, we have it as spherical, and up here would be the highly elliptical. And so what we're seeing is that at the core, we've got something that is quite spherical, and then it's gradually increasing up in ellipticity. And if we compare it to the hydrangea simulation, so this is from Adela's work, we see we're actually going much further in than the simulations, because this is really the brightest cluster galaxy. Whereas over here, we've got the intracluster light. And we can see we're going from low ellipticity, so circular, to actually reaching what we would expect. So the green contours is what we expect from the simulation. So we're able to measure the intracluster light ellipticity to about 10% of our 200. But we really want to go further. And that is why we started stacking. So this is Tuku's latest work. You notice how we got all the position angles of the intracluster light. Well, we rotated all of those images so that the major axis lies along this line, and then we stacked them in redshift bins, and they all have roughly the same mass. So this is the lowest mass redshift bin. There are about 30 clusters stacked in here. The grey regions are where there are too many galaxies that it's actually just masked out. So there's not enough data to get a value there. But what you can see here is actually the intracluster light. So you can see directly the shape of the intracluster light halo. And you can see with your eyes that it is fairly squashed, even at these far out regions. So I'm just going to concentrate on this one and show you what that looks like. So now this is the ellipticity. If this is the H band, and then this is the visible band, so two different bands, and it's slightly different here. But as you could go, we could go much further out. This is the surface brightness profile of all of those different filters. So it's showing you that actually we could reach out to about 800 kiloparsecs, which is almost what you can see with your eye. But now the black points were the same as before. The red points are these red points from here. And what you can see is that we're now able to reach out much further and measure the shape of the ICL halo. all the way out to almost about 50% of R200. So hopefully I'm convincing you that we can actually measure the shape of the intracluster light halo for most of its large extent with Euclid. What we need now is to understand why there's a difference between dark matter ellipticity and the ICL ellipticity, and then we'll be able to translate this curve into a dark matter halo shape. So the last thing I'm going to talk about is about this region down here. You can see that my simulations, we've stopped here. And it's at this point that the data goes down, whereas the simulations seem to stay up. And this is because this is the region in which the brightest cluster galaxy is impacting and really upsetting our intracluster light signal. Remember in this slide, I told you that the stars that form this galaxy didn't form by the same process as these, didn't assemble by the same process as these stars, right? These outer halo stars are closer to the dark matter distribution because they came in the same way, whereas the ellipticity and the position angle of the galaxy really has nothing to do with the dark matter. The problem is that this galaxy is really impacting the area of our halo that we care about most. So remember in this plot, this told us about the different profiles based on the properties of dark matter. Black is cold dark matter, and then our green and blue are different versions of dark matter. The only difference is really seen within this region, and this is RS is 250-ish, so 10% of that, we really need to get to within 25 kiloparsecs to look at the halo, and that's within the galaxy. Here are offsets. They were on the scale of about 4 to 20 kiloparsecs. So I've been talking about the intracluster light, but that's really far out. If we want to use these tests, we really have to do better at measuring inside that galaxy. I'm going to just skip this to go on to the solution. So I think we've got a pilot project that finally allows us to do this and actually extract the intracluster light out from the brightest cluster galaxy. So this is done by my postdoc, Callum Bellhouse. We're going back to this cluster here, Abel S1063. It's a very nice cluster, redshift 0.3, and we observed it with Muse. Well, in the archive, we observed it with 2 pointings of Muse. This is one pointing. So Muse is a square pointing. One of them was there, and the other one was placed there. And they're about 3 to 4 hours on each pointing, actually slightly more one than the other. And we're going to, Muse gives you a spectrum at every single point in this image. We're going to try and use that to kinematically and decouple the Beeson key from the intracluster light. So what we did is we put a very small circle on the center of the galaxy, the brightest cluster galaxy, and we extracted a spectrum, and that's the blue curve you can see there. There is data underneath the blue. There's a sort of light blue line underneath the real data, and the darker blue line, which is the model to that data. We then put a ellipse further out, as far out as we could, and we measured the light there, and that's the red line. You can now see it's a lot more scattered there, but the model fits very well. Now, in terms of the model, we have something that is maximally old for both the brightest cluster galaxy and the intracluster light. However, the brightest cluster galaxy has supersolar metallicity, whereas the intracluster light is best fit something with very subsolar, very low metallicity. Now, that is within expectations, but that means that we have some spectral features that belong to the intracluster light and not the BCG. So from this, we then want to see, well, what's the kinematics of each of these components? So we divide up this region into Voronoi bins, which basically means I sum up the spectrum in each of these patches, and each of these patches is designed to have a signal to noise of 150. It means we get a lot smaller bins in the center and larger bins further out. The reason I'm not showing you anything there is that really there's almost no light there. It's well below 150 signal to noise. So we haven't been able to do that. But we can then look at the kinematics of each of these points. We fitted it with only 2 templates. We could say you could either be a BCG template or an ICL template. So galaxy or intracluster light. We don't fix the kinematics, but what we find is that the brightest cluster galaxy, the ones that are fit to the brightest cluster galaxy, have consistently a velocity dispersion of about 350 kilometers per second, which is very consistent with just a massive galaxy. Whereas stuff that's very old and has subsolar metallicity, it prefers to fit something which has about 600 kilometers per second. There is a third component. That's just because there's some intracluster light that's associated with some galaxies over here that we've sort of separated out. But it's a tiny fraction. Ignore that. The other thing is that the intracluster light and the brightest cluster galaxy have exactly the same kinematics, line of sight velocity. So although they have different dispersions, they're centered on the same point. So it's not like the brightest cluster galaxy is wobbling in velocity space. They're fairly set. And that's just sort of showing you that the bit that's further off, it's just associated with an infalling group that's falling in with 2000 kilometers per second. Okay. So what we did then is we fixed the kinematics to what it was. Sorry, let me go back. We fixed the kinematics. So we said, okay, you've got an intracluster light template. So we know the metallicity, and we've got the brightest cluster galaxy template. So we know that metallicity. We fixed its kinematics to 350 for the brightest cluster galaxy, and then about 600 for the intracluster light. And we said in every single point here, fit those 2 components and tell me how much light belongs to the intracluster light, how much light belongs to the brightest cluster galaxy. And that's what we get out. So this is both a kinematic and a spectral energy decomposition of this image into a brightest cluster galaxy component and an intracluster light component. And here you can see the profile of it, whereas the brightest cluster galaxy is very steep. You've actually got a very flat profile for the intracluster light. And we're able to measure its profile to within about 10 kiloparsecs. The last thing we do is we fit these profiles with ICE-CSIC components, try and get a model. So this is the data. This is the model. This is then the model but binned into the same Voronoi bins as this. So this and this is exactly the same, but we've had to mask regions. And then this is the best fit model. So when you subtract this from this, you get a residual. You can see there's very few residuals. Same with this. This is the data, the model, the bin model, and the residuals. There's more residuals with the intracluster light, but it's still at a very low level. So let me move that out of the way so we can actually see that value. What we find for the brightest cluster galaxy is that it's relatively compact. So it has about a high flight radius of 11 kiloparsecs, and it's also very round. So ellipticity of 0 is a circle, so it's a very, very round galaxy. On the other hand, we have a highly extended intracluster light, so half-light radius of 170 kiloparsecs. Its ellipticity is very high. It's elliptical even in the core. But I'd like you to notice that the best fit model actually refuses to put the center on. It's very hard to see, but that's where the cross is. And the offset is about 8 kiloparsecs off. So we're actually measuring an offset between the brightest cluster galaxy and the intracluster light halo, which we think traces the dark matter halo. So it looks like we've actually detected this BCG wobble there. Oh, I've touched it, so it's not going to work. There we go. So I just wanted to bring back, this was the ellipticity from the Euclid images, the stacked images. And I just wanted to show that the reason why we're getting this low ellipticity in the core is generally because we've got a lot of this light dominating the very central regions. And it's only as we get further out that we see this. So the only way we really decompose them is by using this kinematic tracer. So we need things like the large IFUs, integral field units, in order to spectrally decompose those. So a bit of a summary of just this project. We're finding that the intracrustal light, it's very diffuse, but it's actually the dominant component. So about 75% of the light within 100 kiloparsecs comes from this component. It's really bright here, but there's very little space here compared to this region. And actually, it's most of the light within 500 kiloparsecs. We're very excited that we can actually measure this offset of 8 kiloparsecs, and we can measure the profile of the intracrustal light. Here it gets really dodgy. It becomes very hard when the brightest cluster galaxy is so much brighter than the intracrustal light. But in this region where they're comparable, so up to about 10 kiloparsecs, we can actually measure the inner profile of the intracrustal light, and hopefully the dark matter halo. And why that matters is because that's where we see the difference with the self-interacting dark matter. And here we can see the range of different wobbles, brightest cluster galaxy wobbles. Now with one cluster, a wobble of 8 kiloparsecs could be anything, right? It could be cold dark matter, it could be self-interacting dark matter or fuzzy dark matter. The reason why is that really you've got a distribution. What we need to do is to apply this to tens of clusters to then be able to see that. Right, so that takes me up to my conclusions, in fact. So the intracrustal light does trace the dark matter halo. However, it doesn't do so exactly. There is a difference in the orbits of the particles, both in energy and also in angular momentum. If we want to use intracrustal light as a direct tracer of the dark matter halo, we really need to understand why. And I think we're close to doing that. I think doing that with the simulations will allow us to do that connection. But that is the next step. We've managed to process 200 clusters with Euclid, preserving the intracrustal light. Hopefully, I've convinced you that we can actually measure the shape of the halo quite far out, about half the R200, so half of the virial radius. The next step is that we apply this to DR1. So we can't actually do the cosmology with 200 clusters. We need a much larger number of clusters to actually measure the distribution of their shapes. And so that's why when we get the next data release, we plan to observe about 12,000 clusters. And that will be the first time we can actually do the cosmology tests. And then I've shown you really nice work that's the kinematic and spectral decomposition of the brightest cluster in ICL. And that is the method that allows us to see the core of the dark halo. However, that takes a lot more telescope time, and it does need to have tens of clusters. So I've showed you the pilot project. Hopefully we'll get more data on this. So thank you very much for your time.
Okay, questions for Nina?
Whenever you compare PCQ or whatever hydro, how much does it depend on how the hydro is? How you do the feedback, how you do the propagation, how the revolution?
Yeah, it does matter. And I know this because, okay, the resolution is, it's vital you're able to, the dark matter resolution is high enough that the galaxies don't just poof as soon as the merger happens. And so the resolution matters. If the galaxy just poofs, sorry, when I say poof, it means that the stars disintegrate at the same time as dark matter. Then there's almost no difference between the dark matter distribution and the intracluster light distribution, because in the simulation, they're getting assembled in exactly the same way. So you only see this where the resolution is high enough. However, does it matter in the galaxy astrophysics? It might do. And it's only becoming clear now. My students showed me the ellipticity of horizon AGN compared to the ellipticity of hydrangea, and they were just slightly offset. And I don't know why. It's very hard to pinpoint why there are differences, whether it's in the feedback or anything else. But that is a problem. And I haven't quantified it yet. But our next step is to quantify how much the feedback of the galaxy physics, the cooling, actually impacts this. In principle, it shouldn't be too much.
Are the sizes of the galaxies in each simulation
Are they
different?
No simulation can adequately produce a disk galaxy. So the sizes are not that different, but I wouldn't say the shapes of the galaxies in simulations are realistic.
But then that's, if the shapes are not realistic, that's actually matters when you strip the stars, right?
Yeah.
It's not the same as if you strip the stars in a disk than in a sphere.
Yes. Yeah, it is. So that would matter. Okay. What helps us is that actually most of the intracluster light comes from, remember that movie in which I showed it's the violent relaxation. It's the point where the massive galaxy is actually just smashing into the brightest cluster galaxy. And for that, it doesn't really matter so much.
But if they come from massive satellites, which are Milky Way, those are disks.
Yeah, then it would be a problem.
Maybe a question. I assume that the VCG galaxy should be a massive galaxy. But if we go to higher redshift, or if it is possible that the brightest galaxy being a low mass galaxy, it is possible to see if the intercluster light could give us some clue about the castor problem.
So if it would be great if that was the case, but if you have a low mass brightest cluster galaxy, most likely you also have very little bright intracluster light. And that's because the growth of the brightest cluster galaxy is in step with the intracluster light. Some of the mergers go in to assemble the brightest cluster galaxy, and the rest of the light goes into the intracluster light. So generally, you build up your massive galaxies first or at the same time as the intracluster light. So what people tend to do is they tend to go down to the dwarf galaxies to try and look at the core cluster problem in those cases rather than the VCGs. VCGs are not a very good place to look at the core cluster problem, but I think we could do it with this decomposition.
Yeah, normally when you look at low mass galaxies and dwarf galaxies, you see that they are cored instead of what you expect that would be Caspic. But still, it could be feedback, the stellar feedback, or it could be different flavor of dark matter. So we're still there fighting in that.
Yeah, the reason we want to look at it in clusters as opposed to dwarf galaxies is that feedback can really affect the halo of a dwarf galaxy, right? The galaxy has a big impact on the rest of its halo. It's massive. Whereas in a cluster, it shouldn't have so, like, really mostly dark matter dominated a lot of region. So it should have less effect. It's still not a great place to look.
Elizabeth?
Does the same, but they make it in around. So how can
We need very good, okay. So we're hoping to use tracers like the X-rays to try and strain the feedback models that will allow us to know how much this particular cluster has had in terms of its feedback. And then we can look at intracluster light and look at the halo for that particular feedback model. However, it is correct that a different amount of feedback could give us different things. That said, I think the X-ray observations of clusters are actually becoming really really constraining cluster astrophysics a lot more nowadays. So I'm hopeful that would work.
Whenever you do axis ratio, the axis ratio at least in dark matter comes from the mass. So
Yeah.
whenever you do the stacking, do you take into account how much, what the difference in mass in whatever you stack or not?
We will do. In what I've showed you here, which is, yeah, it was 30 clusters. The reason why it's 30 clusters is we picked everything that was just between 1 and 3 times 10 to the 14 solar masses. And that was the most that we could do, just because we only had a sample of 200. Also, the masses are not that well constrained at this point. The next version of Euclid cluster catalog should have masses determined by weak lensing. So we should be able to get a much better stacking. So we want to divide it up, not into only into redshift, but also into bins of mass determined by the weak lensing, and also some kind of idea about its dynamical state. So the more relaxed and the highly merging clusters. That should allow us to then really see the shape of the halo for these different sets. But yeah, more massive clusters tend to be more elliptical than the low mass ones. So that's why we do have to separate them out. But currently, we only have a few tens. So we just stack them all together.
More questions for Nina? No? If not, let's thank Nina again. Elisa? You know the paper of Gonzalo that you said?
No way.
Jeez.
Ah, you should show me.